Next up, video 2, we're going to talk about that special chi-squared goodness of fit test. Now, in total this chapter, there will be 3 different chi-squared tests. This is part 1. So in yesterday's video, we mentioned there is a single test that can be applied to see if the observed sample distribution is different from the hypothesized population distribution whenever we were talking about the M&Ms. The company may claim, hey, these are the percentages of colors that you should expect to see in a bag of M&Ms, but is that necessarily what we will see when we actually open up a single bag of M&Ms? Not necessarily. Okay, so we talked about, this is leading up to what we're going to be discussing today. We can actually now see if what the company says is statistically true or if it is statistically false. So the example we're going to look at says, in recent years, the expression, the graying of America, has been used to refer to the belief that with better medicine and healthier lifestyles, people are living longer, and consequently a larger percentage of the population is of retirement age. We want to investigate whether this perception is accurate. All right, so here I have information about the population in 1980. So I've got it broken down by 4 age groups here. And here's how many are actually in the population for each of those 4 age groups. And here are the percentages for each of those groups. So together there is my full 100%. Now, I want to see if this really holds true still in 1996. Okay, we're going to go back in time. This is a hot tub time machine. We're going to go back to 1996 and randomly select 500 individuals. And we're going to see how old these 500 individuals are. So out of our 500 individuals, here's what we found. 177 of the 500 were 0 to 24. 158 were from 25 to 44. 101 of them was from 45 to 64, and 64 were 65 and older. Now, I could make a segmented bar graph and look at, here's my population as percentages right here. And then here is my individual counts right here. So you can see here, comparing our 2 segmented bar graphs, that, these 2 groups, this is the population, this is our sample, they're pretty close to each other, right? And these 2, this one's gotten bigger, this one's smaller, this one's about the same size, and our 65 and older, it's gotten a little bit bigger. So really we went bigger, about the same, bigger, smaller. So we have fewer 0 to 24-year-olds in 1996 than we did in 1980, which means people are getting maybe older here. We're allowing for more growth up top here. So it seems like it might be plausible. Maybe better medicine and better, healthier lifestyles is producing longer life. But that's what we're going to test. So our hypothesis, and we're still going to do kind of the 4-step process with this. We're going to have hypotheses, conditions, calculations, and conclusion. So our hypothesis, our null, is that the distribution of ages in 1996 is the same as the 1980 distribution. Okay, so we're going to assume first that these are roughly the same, that they are roughly equal. Alternatively, we want to show that the ages in 1996 are not the same as in 1980. We're not going to specify direction here. We're not going to say that the ages of one is greater than the ages of the other, because that really wouldn't make sense. Think back to the M&M example. If we were shortchanged on the blue, that meant we were overchanged, I guess you could say, in other colors. So we're not going to break it down by age group when we do this. Again, you would have to do 4 hypothesis tests if you wanted to test each age group. Okay? But we're going to look at this kind of as a collective unit. So either the distributions are roughly the same statistically, or they are not the same statistically. Our conditions, 2 of them are still the same. There is still a random condition, there is still an independent condition, but the normal condition changes. And it's really going to be easier for you, to be honest. So we also need to ask, well, first we need to ask ourselves, are we dealing with a random sample? And it specifically said on the last page that there were 500 randomly selected individuals. So we're good there. The independent condition, you're still going to be asking, is the population at least 10 times the sample size? where our population is all US people from 1996, because that's when our sample was taken. And we sampled 500 individuals in 1996. So 10 times that makes 5,000. Can we assume that there are more than 5,000 people in the US in 1996? Of course there are. Large sample size is going to be the name of our third condition. And all we're going to have to check is, are all expected counts at least 5? Well, we don't really know the expected counts at this point. So you can go ahead and write this, and we're going to have to come back later and verify that this is true or not. Okay? I almost feel like you could do the calculation part second and then the condition part third before you write your conclusion fourth. So now let's jump into the calculation part. Okay? So again, here's our observed counts. This is actually what we saw out of 500 people. And our expected counts, all we're going to do is take our 500 people, remember all of this added up to be our 500 people, and we're going to use the percentages back from no, is that right? Yeah. Okay. I got to figure out something here. These percentages aren't from 1996. These percentages are from 1980. Okay, so if you go back and look here, those percentages from 1980, that's what I clumped together here. So really, it's almost like this needs to be completely separate. Here is our sample from 1996, or 1996 sample, we'll say, and these percentages over here are percentages from 1980 from the population. I was getting myself confused there. Okay, so now, out of 500 people, we would expect, assuming the null hypothesis is true, that 41.39% of 500 people should be from 0 to 24. So we multiply that, and we would expect 206.95 people out of 500 to be 0 to 24. We actually observed 177. So we keep doing the same thing. Out of 500, we would expect 27.68% to be 24 to 40, or 25 to 44, which is 138.4. And keep going on down the line here. And here are all of our expected counts. Now, to use our chi-square formula, observed minus expected squared divided by expected. So I'm really going to take 177 minus 206.95. It'll give me a negative value, but when I square it, it makes it positive. And then we divide by the 206.95. And you should get, and I did more decimals here than just 4 sig figs, but you can cut it off, right here. We'll say 4.334. And keep doing the same thing. Now I get 2.7757, 0.0798, 1.0241. Add up all 4 of those numbers, and here is my final number that I'm really looking for, so I can use some calculations with. That is my total chi-square number. Now, which individual chi-square observation contributed the most? That would be this guy. So I had the biggest amount of change in my 0 to 24 group. And I had the least amount of change in my 45 to 64-year-old group. I expected 98.2 of 500 people to be 45 to 64, and I saw 101. So there was a very small difference between what I observed and what I expected. Now, just like before when we had a z or a t-score, we needed to give value to it. So now we're going to find what is the probability that we find other chi-square scores, statistics, that are more extreme or as extreme as our 8.214 that we got here. Now before we would use normal CDF, t-CDF. Well, now there's a chi-square CDF. Just go to look at second variables where distributions are, and you should find chi-square CDF. And it's going to work just like t-CDF. We need a lower bound, an upper bound, and degrees of freedom. So our lower bound will always end up being this chi-square number. Because remember, our chi-square numbers will always be positive. So we're always going to go from that number to infinity. Oh, crap. There we go. So 8.214 to infinity. Now degrees of freedom, notice up here. Degrees of freedom is going to be equal to the number of groups minus 1. And here we have 4 groups of ages. So 4 minus 1 makes 3 degrees of freedom. Type that in and you get 0.0417887, which is less than our alpha value of 0.05 that we're going to assume is in place. Do you guys hear that noise? That's the janitor going down the hallway. That is so loud. It's crazy. And we would reject the null hypothesis at that point. So our conclusion, oh, you know what else we need? If we use chi-square CDF, we need a picture. So now let's come down here. Draw a half x, half y axis here. What do we have? 3 degrees of freedom. So that means our peak is going to be at 1. So we're going to have something that maybe looks like this. You know, here's where 1 is located. And we are at 8.214. Man, we're way down the line here. So here's where 8.214 is located. We're going to shade beyond it, which makes sense that we get a very small answer for that part. So our conclusion, just like we did for hypothesis testing, we do have enough evidence at the 0.05 alpha level to conclude that the distribution of ages in 1980 is not the same as it is in 1996. Now, you might go, well, 45 to 64, it pretty much was in line with 1980 to 1996. But overall, we're saying that it's not. Again, we're not picking on specific groups here. We're saying overall, as a collective group, things are not the same as they were from 1980 to 1996. And really, our biggest contributor are our young people, okay, and even the next youngest group, okay. These two together contribute, you know, over 75% of our chi-square value here. So it's really looking like these values are significantly larger because what we observed was larger than what we had expected. And it's contributing a lot to our chi-squared, which allows us to reject our null hypothesis here. Now, here is your problem to do and bring tomorrow to class. Yes, oh my gosh, this is a lot of writing. Get over it. Just read it, okay? The one thing that I have kind of shrink down here is this Punnett Square, which really isn't entirely necessary, but if you must see it, there it is. Now, again, bring this tomorrow to class, worked out. I did give you a hint down here at the very bottom. I give you what the probabilities are for each of the 4 different types of, I don't know what we're even looking at here, some sort of moth or something. I don't know, fruit flies. There we go. All right, so have fun with that. Bring it tomorrow to class. We will check it and we will go over it. Adios. See you at video 3.